radiation sail. Thank you. Different kind of radiation sail. My name's Ron Bennett, aerospace industry. I'm retired. Did a lot of stuff in my life. It's my project here. I didn't know if I was going to make it tonight because health issues, so I made it into a movie format. It's about 20 minutes long, so I'll start that now. It explains everything in detail. Can you hear that?
Yeah.
Can you hear it?
Quiet. It's just music, right?
No, it's more.
Okay.
What counts is not what sounds plausible, not what we'd like to believe, not what one or two witnesses claim, but only what is supported by hard evidence, rigorously and skeptically reasoned. Extraordinary claims require extraordinary evidence.
Cosmic realm of things, Mars is just a stone throw away from the sun. The fastest we can hope to travel there is chemical rockets, so it'll take us at least 6 months. Okay, let me pause this. All right.
Turn that off. Turn your mic off.
Oh, okay.
That's why I plugged it down, because that was feeding back from the... Okay, you can play it again.
I'll do this turn off. They're faster, but that requires building a massive auxiliary power supply or building a huge solar cell. I came up with a new alternative nuclear propulsion system. It depends on nuclear fissionable material, but not the way we used nuclear power before. This is my extraordinary claim that can easily be tested out in the nuclear lab on Earth. We don't need to spend $100 million to launch it into space to see if it works. And if we find that extraordinary evidence, which I'm searching for, from our research in the lab, that this proposal works as predicted, Mars will not be so far away. The stars will be reachable within a generation. That's extraordinary. In the nuclear reactors, some of the radioactive decay particles, alpha, beta particles, are expelled from the decaying atom, turning kinetic energy of the particle into thermal energy when it collides with another atom within the mass. However, gamma and slow, fast neutron particles mostly escape the mass. Over 99.99% of decaying alpha particles will never leave the mass. The decaying ejected particle will strike another atom within the mass, therefore turning the kinetic energy into thermal energy. Now, if you take that same mass, spreading it out over a large surface area in a thin film, thin enough that most all the decaying particles are expelled from the atom, will randomly exit the mass by either going up or down out of the nuclear material. Therefore, if you shield one side of that thin decaying nuclear material and leave the other side unshielded, on the shielded side, the decaying particles will strike another atom, turning kinetic energy into thermal energy. On the unshielded side, the particles will exit the mass as thrust because the atoms that decayed from will recoil in the opposite direction, with the exhaust speed of the decaying exiting particles up to 99% the speed of light. For every action, there's an equal and opposite reaction. Just one particle doing this, then the reaction is not noticeable. However, trillions of particles per second, per gram, all add up. Alpha particle emissions are extremely ionizing. Therefore, the interaction with other atoms slows it down fast. For example, high-speed decay in alpha particle, that's a helium atom without electrons, in air can ionize as much as 1 million atoms within a couple centimeters by pulling an electron out of orbit around the atoms that it comes close to. So therefore, folks, alpha particles in air can only go a few centimeters before it slows them down real fast. Most alpha particles with kinetic energy of 5 million electron volts or less can be stopped with a thin sheet of paper because they are highly ionizing. Therefore, a solar cell can be constructed using alpha particles emitting radiation only, like plutonium-238 with solar cell thickness of 0.1 millimeters, 0.004 of an inch. They can be used and shielded one side of the thin nuclear embedded material. In the following demonstration, I'll use beta particles, which is mostly fast-moving electrons, to help explain my madness. Beta particles cannot be stopped by a thin piece of paper. However, they can be stopped by a plate of aluminum, depending on the kinetic energy, up to about 400 centimeters thick, or over 150,000 inches thick. When a beta particle decays, it's said to electron tunnel through some of the mass. So the true depth of some of the penetration from just under a surface material is undetermined. If you look at the speed of the beta particles, they are all going about the same speed. Therefore, there must be some kind of tunneling underneath the surface. For example, by using strontium-90, yttrium-90 decay embedded in a thin large surface area at 1 meter square, strontium-90 half-life is 28.8 years, which decays into yttrium-90 that has a half-life of 64 hours, about 2.5 days. Yttrium-90 decays into stable zirconium. The reason I'm using SR90 and Y90 decay because of its readily affordable and availability. Pu-238 isn't as abundant and affordable. Strontium is extremely dangerous. It's similar to calcium in that it is readily absorbed into our bones. You can easily get bone cancer if you inhale or get it into your blood system, which would absorb into your bones. Yttrium-90 is not as dangerous. In fact, it is used in cancer treatment. I'll explain in greater detail about the amazing properties of yttrium-90. Therefore, I'm seeking the extraordinary evidence to back that claim up. It's just like basic physics in the lab. First you do the math, then you do the experiment to back up your math claim. I did the first part. Now I need to do the second part to see how my experiment ends up that backs my math claim. However, I can't do the experiment without the help of a nuclear lab. As a result, after doing... Here's a chart that shows the power density in RTGs, isotopes, per gram. Notice plutonium-238, which has a 0.56 watts per gram. Because plutonium-238 is one of the easiest one, health-wise, to work with, NASA uses isotopic thermoelectric generators. Plutonium-238 watts per gram is easy to calculate because 100% of the kinetic energy is alpha particles. This is how you calculate that out. Now, look at the chart again. Plutonium-238 is way down the list. Yttrium-90 isn't on the chart. Why is that? It's a part of the strontium-90 decay in this chart. But it's a very minute amount in yttrium-90 that decays and makes power density twice as much as what it should be calculated at. This is why yttrium-90 decays results in 100% beta particles. Like plutonium-238, its power density is easily calculated. If it was included in the chart, this is what the chart would look like.
Use the force, Luke.
Say what?
Use the force, Luke.
I'm sorry, I think you got the wrong number.
Okay, sorry.
Now this is where it gets to be a lot of fun working with these numbers, folks. The real reason I picked on strontium-90, radium-90 decay in this presentation is what makes the extraordinary climate at the beginning more positive. Remember the other radiation mathematics I'm trying to work, so it isn't just dependent on Deuterium-90 working as described below. The extraordinary time includes reaching to a near star system within 25 years, 2.5-day trip to Mars. After doing the math, it jumps right out at you. Let's look at the numbers here, folks. In 1 gram of pure Yttrium-90, there is 2 times 10^16 electrons per second decaying. That's 20,000 trillion decays every second. 1 Yttrium-90 beta particle has a kinetic energy of 2.2 million electron volts, which means in 1 gram of Yttrium-90 there is 7,305 joules per second, or 7.3 kilowatts of energy. This is only 1 little BB-sized gram of pure Yttrium-90. Even though Yttrium has a very high melting and vapor point, if it was pure Yttrium-90, it would be so hot that it would vaporize that gram of Yttrium. So it doesn't have to be pure Yttrium to make it work for us. Now let's compare that to the known energy when firing a bullet. A 9mm, 7.5 gram bullet casing, when struck by a pin, releases about 467 joules of energy, propelling the bullet to about a little over the speed of sound at 400 meters per second or more. As a result, 1 gram of Yttrium-90 has about 16 times more energy per second than is fired from 1 9mm bullet casing. So imagine it's accelerating for 230,000 seconds, constant acceleration at high G forces, above what even a human can stand. That's amazing. Someone is going to tell me that by the time you install on a rigid sail, it would have already decayed. Yeah, but here is where it's going to get fun, folks. Yttrium-90 decays into stable zirconium, which also has a high melting point. As a result, if all the Yttrium-90 decayed, then what you're left with is stable zirconium. Because Yttrium-90 is used for cancer treatment, businesses were looking at how to make it artificially. They had to extract it from strontium-90, which is, as I said before, very dangerous for bone cancer. If just a trace of strontium-90 and yttrium-90, then it would be dangerous to the patient. Therefore, they took some zirconium, shot a stream of neutrons at it. Each neutron had a kinetic energy of over 12.1 million electron volts. Guess what happened, folks? The stable zirconium captured the neutron and produced a small quantity of Yttrium-90. Yttrium-90 decays into zirconium. Zirconium, when fed a stream of fast neutrons, turns into Yttrium-90. When that Yttrium-90 decays, it turns back into zirconium. Therefore, zirconium can be used repeatedly to charge up the battery. Once you saturate that with fast neutrons, you got 2.5 days or more to use it, and then battery runs down, you resaturate it with fast-moving neutrons. If this proves out in a lab, then this is where it gets a little spooky, folks.
A reasonable sized circular shaped object freshly covered with enough Medium-90 has more than enough force to lift off of Earth's gravity well and into space. Now, it's got enough G's to travel up to 98% the speed of light in a relatively short time. That means because the G-forces are so strong, can be, depending on how much mass you put on there and how you control it, that it'd be too strong for humans to even endure. Slow that down to 1G, constant 1G acceleration, halfway to Mars, and deceleration halfway the rest of the way there to slow it down for Mars orbit. Then guess what? It's a 2.5 day trip from Earth at Mars' closest approach. This is where I mentioned another patent of mine that is not patent pending. So I can tell you how we can charge up most of the zirconium coating, turning it into yttrium-90 in a very, very short time at a reasonable cost. A spaceship with surface coating of zirconium with parabolic shaped surface where a fusion reaction beam is placed at its focal point. The fusion of the atoms releases a tremendous number of neutrons with kinetic energy of over 14 million electron volts. It's fast enough to charge up most zirconium coating, turning it into yttrium-90. A fusion producing neutron emitting power supply source that saturates the zirconium surface with high-speed neutrons, with each neutron having over 12.1 million electron volts of kinetic energy. When traveling to the stars, we can use several different radiation types on our spacecraft with the fusion-induced yttrium-90 rigid cell for extra force. The zirconium fusion-induced neutron reactor will use sparingly when we need extra force because of the amount of extra mass needed for the fusion reaction pellet we must take with us. The other radiation type with less force wouldn't need extra mass and has many years of half-life in it. The second method. NASA proposed Project Orion nuclear pulse drive, where scientists postulated that we can go to the stars by using small nuclear bombs exploding behind the spacecraft in quick succession instead of using nuclear bombs as propulsion. Only use small hydrogen and neutron bombs to charge up the zirconium, producing almost instant saturation of high-speed neutrons under the zirconium coating all at once. You would only have to explode enough to saturate the needed amount of zirconium every 3 to 5 days until you reach your desired speed. Then the other radiation embedded on some of the other surface area will take us the rest of the way there. Now, you ion drive people, I'm going to drive you crazy. An example of how that would work for alpha particle ion drive in an experimental spacecraft is 1 gram of plutonium-238 would be spread out over 314 square centimeters. Disc-shaped object with a 10 centimeter diameter. By using radioisotopes spread over a large surface area with plutonium-238, by running a high voltage through its anode, which will repel the alpha particles and the ionized particles. One way is to use a thin layer of radioisotopes spread out over a large surface area for other developed uses of ion drive engines, such as a Hall thruster. The shielded obstructed side is producing electrical energy from the RTG, radioisotope thermoelectric generator, Stirling engine or a steam engine or a steam turbine in thermal energy. By using the generated electrical energy from the thermal energy, the electricity can be provided high voltage needed to use in the ion drive. No need to lug around a huge power plant for energy. Half of the radiation is solar, and the radiation cell is making its own electricity.
This way you are conserving most of the energy. One question people are going to ask, and I'm prepared for it, is how are you going to control all this from the radioisotope decay? How are you going to do that? Well, here's how we could control it. All you got to do is open or close the area that's being decayed, and the kinetic energy is conserved. Opening is wide all the way. You got full thrust. You close it half a way. You got 1/3 thrust. And if you close it all the way, you have no thrust. That's how you can control the amount of force when you're landing or taking off from a known area that you're exploring. So I got a lot of work ahead of me. I know that. I know this is an extraordinary claim. So now I got to do some lab work. NASA has spent billions of dollars on ion drives, solar cells, with maximum speeds of 40 kilometers per second. The maximum speed of a radiation cell is 296,000 kilometers per second. Just a little bit of funding, we can prove this out in the lab. We don't need to spend $100 million to launch it into space to prove some of its claims. It won't take us 40,000 years to reach our nearest star, or 9 months to travel to Mars. Our next goal is testing several parts of this out, including different radioisotope ion drive configurations. In this presentation, I made several extraordinary claims. I understand that. I proved out the math. Now let's find the extraordinary evidence to back up some of those extraordinary claims.
And that's all, folks.
Is there any questions? Go ahead.
What kind of radiation shielding would you envision if this were used for manned space travel?
Well, as you can tell, there wouldn't need to be much radiation shielding you need at all, because you're not talking about gamma rays or unless you use the neutrons to charge up. You're not talking about gamma rays, but in space you got cosmic rays and a lot of other things. This can alpha particles can be stopped by a sheet of paper, so the spacecraft can do it. Anything thicker than 150 thousandths or 400 centimeter thick aluminum, beta particles can be used. So you don't need that. In fact, you can put the spacecraft that you're taking in the middle of all this, and it can help provide you with a magnetic field that stops or deflects some of that radiation coming in from space. So that's one way to look at it. Yeah, go ahead.
Is it possible to, it looks like it is possible to prove your claim on Earth? You don't need
Oh, I'm glad you asked that, because hoping somebody would ask. You're in a lab. You coat a surface with a thin layer of, let's say, a thin layer of strontium-90, because it's real cheap for radioisotopes. That's one of the cheapest. And of course, you have all your equipment to protect you. But you just put it down on a scale. You scale it. You weigh it. You know what the mass is. So if your mass is less than what you have on the scale, then that will prove it out. That's as simple as that. So it's got a little bit of levitation, but not strontium-90, but not enough to lift. But yttrium-90 does. In fact, yttrium-90, in 1 kilogram of yttrium-90, and that's what they base Newtons on, there is 7 megawatts per second. So it's a continuous half-life of 64 hours. So you got 9 megawatts in 1 kilogram But if it's together, it would disintegrate. But spread out in a real thin film, where you got heat exchangers and all that, and modulators, then it will, you can do it. But I got to prove it in the lab. So there you go. I think I'm done.
Okay,
Thank you.
wonderful. Give a hand.